So we're going to put all this together to find the real zeros of a polynomial. Here we know the polynomial is of degree what?
3.
It's 3. Therefore, there are at most how many zeros?
Would it be 3?
Yep, there are at most 3 real zeros. So as soon as you find 3 zeros, you're done. You know you can't find any more. Use Descartes' rule of signs to determine the possible number of positive zeros and negative zeros. And so remember, with Descartes' rule of signs, for the number of positive zeros, what we do is look for the number of sign changes from positive to negative in f of x. So for example, here I'm going from a positive 3 coefficient to a negative 5. So that's one sign change. Here, no sign change. And here I'm going from a negative to a positive, so there's a sign change. And so we would say there are 2 sign changes in f of x. Therefore, there are 2 or 0 positive real zeros. So it's always the number of sign changes in f of x or that number less than even integer until you get down to 1 or 0, because you can't have negative number of zeros. And then remember, for the number of negative real zeros, what we have to do is evaluate f of negative x. So that's going to be 3 times negative x all cubed minus 5 times negative x all squared minus 4 times negative x, and then plus 4. So negative x all cubed is negative x cubed. So this is going to be negative 3x cubed minus 5x squared. A negative 4x, negative 4 times negative x is plus 4x, and then plus 4. So here I'm going from negative to negative, so no sign change. And then I'm going from negative to positive, one sign change. And then positive to positive, no sign change. So I only have one sign change in f of negative x. Therefore, there is one negative real zero. So I know for sure there's only one negative real zero. I'm not going to look for any more than that. That's nice, right?
Yeah.
Yeah, it is. Okay, now here's where it gets a little bit more challenging. What we have to do here is first find the potential rational zeros. So my part C is going to say list the potential rational zeros. So remember, to find the potential rational zeros, the first thing we do is write P, the factors of the constant. My constant here is 4. So you ask yourself, what numbers, when I multiply them together, give me 4? What do you got?
1 and 4.
Mm-hmm. So plus or minus 1, plus or minus 4, and then the other possibility is 2 and 2, right?
Mm-hmm.
So 1 and 4 or 2 and 2, and don't forget the plus or minus piece. And then we write Q. Q is the factors of the leading coefficient, which is 3, right? There's only one thing you can do there, plus or minus 1, plus or minus 3.
So you always have to write it down for the first coefficient and then the last one?
Yes, that's it. You ignore everything in between. Yep, so it's only this guy here. The leading coefficient are the factors of Q, and then the constant are the factors of P.
Okay.
And now what we're going to do is form all possible ratios of P over Q. So remember we do there 1 over 1, 2 over 1, 4 over 1. And then we do 1 over 3, 2 over 3, 4 over 3, like that. So here we go. 1 over 1, 2 over 1, 4 over 1, 1 over 3, 2 over 3, 4 over 3. So remember what this theorem says. If the function f is going to have a rational zero, it must come from this list. So again, 3 is not in this list, so I know for sure 3 is not a zero. -2 is in the list, so -2 might be a zero, but it might not. We don't know. Okay? So what we're going to do here is you have access to a calculator. And so what I recommend that you do is graph this function on your calculator. So all you have to do here is graph the function, and it'll help narrow down the list for you. So what did we have? 3x cubed. I don't remember the function anymore. Minus, make sure you use f of x, not f of negative x too. Minus 5x squared. Minus 4x, it was plus 4, I think, right?
Yeah, I think so.
You can tell from the graph now that it looks like I'm crossing the x-axis at -1. It looks like I'm crossing, I don't know, somewhere between 0 and 1, and it looks like I'm crossing at 2. So notice this was a polynomial of degree 3, and it looks like we're going to have 3 real zeros. Remember, we said there's only going to be 1 negative real zero, and we said there's going to be 2, which we see, or no positive real zeros. Right? So all the analysis that we've done up to this point is playing out for us. It looks like -1 is a 0. There is a 0 between 0 and 1. There is a 0 at 2. I'm not going to say there is, but it seems. All 3 are odd multiplicity. I know that as well, yes? I know that because they're crossing the x-axis, right? If it was just touching, then they would be of even multiplicity. This is a visual suggestion. It's not, so it's evidence, but it's not proof. To prove that, say, -1 is a 0, we use that factor theorem. So if -1 is a 0, then it must be the case that f of -1 is going to equal 0. So we just have to verify that that's the case. So we're going to evaluate this function at -1. -5x squared minus 4x plus 4, minus 4 times -1, and then plus 4. So this is going to be -3 minus 5, -1 times -4 is plus 4, and then plus 4. So -3 minus 5 is -8, and 4 plus 4 is 8, so I'm getting 0. Because -1 is a 0, we know x minus a -1, which is x plus 1, is a factor. We want to find the two other zeros as well, but we also want to completely factor this. So to completely factor this, we use the division algorithm. We're going to divide x plus 1 into the original function f to factor it. And I recommend totally using synthetic division. It's just a ton faster. So remember how that works. You put your value of c outside, and then you put your coefficients underneath. 3, -5, -4, and 4. Because remember, the polynomial was 3x cubed minus 5x squared minus 4x plus 4. With synthetic division, you bring down the first factor, the first coefficient rather, which is 3, and then you do multiplication. -1 times 3 is -3. -5 plus -3 is -8. And then repeat. -1 times -8 is +8. And then add vertically. -4 plus 8 is 4. And then -1 times 4 is -4. Add vertically, you get a remainder of 0. The values across the bottom down here represent the different coefficients in your quotient. So this is the remainder, the constant. This is the coefficient on x, and this is the coefficient on x squared. So this is the remainder. That's always the constant. Coefficient on x, coefficient on x squared, and it just keeps going up by 1 degree. So then x cubed, then x to the 4th, so on and so forth. And so what this means is that the original polynomial, which is f of x equals 3x cubed minus 5x squared minus 4x plus 4, can now be written as x plus 1, your divisor, x minus a -1 technically, times the quotient, 3x squared minus 8x plus 4. So it's the factor, x plus 1, and then the quotient. So, because remember the division algorithm says that f of x can equal q of x times g of x plus r of x. The polynomial is the quotient times the divisor plus the remainder. Our remainder is 0, so we don't have any value to add in. Technically, it's plus 0. And now with these problems, at this stage, you have two options here. Option 1 would be to go back to your potential rational zeros in your graph and work with this expression right here. That's called the depressed equation. Or what you could do is look at it and say, all right, well, this is a squared value, so I'm going to attempt to factor that particular expression. And if you tried to factor it, I think you'd be successful. The only way to factor 3x squared is 3x and x. And if you write -2 and -2, you get the factored form, right? Because this is minus 6x minus 2x gives you the minus 8x in the middle. So now that's the factored form. And from that factored form, you can see what the zeros are, right? Because x plus 1 is a factor, -1 is a 0. Because 3x minus 2 is a factor, what's the 0 going to be? Well, you can just solve like this and get that 2/3 is the 0. And because x minus 2 is a factor, 2 is a 0. And if you went back to your potential rational zeros, 2/3 is in that list. So that should make you feel better. right? If you ended up with something like 3/4, you'd have to worry because 3/4 wasn't in your list of potential rational zeros. And so there you have it. This is the factored form, and here are your zeros.